Hello, and welcome to today's WJE webinar. My name is Liz Pimper, and I'll be your moderator for this webinar, Now Approved, Understanding the IBC's Tall Wood Building Provisions. During the next hour, WJE Fire Protection Engineers Carl Baldassarra, a member of the ICC Ad Hoc Committee on Tall Wood Buildings, and Tim Costello will provide an overview of the new code provisions concerning mass timber buildings, including allowable heights and areas, fire resistance ratings, allowances for exposing the timber structure and/or encapsulating with non-combustible materials, options for utilizing concealed spaces, and more. This presentation is copyrighted by Janney Elsner Associates. And now I will turn it over to Carl to get us started. Carl?
Thank you, Liz, and welcome everyone. We're happy to be able to present this webinar to you today. This presentation will cover a general overview of tall wood buildings, a number of those that are proposed and some that have been recently built, and you'll see what's driving the demand for these buildings. We'll cover a review of some of the research and testing that was done to develop the IBC provisions for the 2021 code. And we'll talk a little bit about the code development activities themselves that led to the new provisions. Learning objectives. First, at the end of this program, you'll be able to understand the different types of mass timber construction in the 2021 edition of the IBC. You'll be able to assess the different construction types that are appropriate for various uses and heights of buildings. You'll be able to identify the key passive fire resistance requirements and the active systems that are needed to enable the use of taller and larger mass timber buildings. And you'll be able to understand the technical bases for the code changes themselves. An outline of today's presentation. We'll have an introduction. We'll talk about some of the major issues that are affecting tall mass timber buildings. I'll bring you through the activities of the ICC Ad Hoc Committee on Tall Wood Buildings. Tim will talk about the major changes and some of the other changes. We have a case study, and then at the end we'll have a summary, and then of course we'll take your questions and answers. So, you've undoubtedly seen much in the news about tall timber buildings recently in technical publications and architectural digests and various publications. And some of them have some very catchy headlines like this. But to folks in the fire safety business, this new technology presents some pretty significant challenges for fire safety. This is a building that, when it was under construction in Minneapolis, what's now a 7-story, 220,000 square foot building, known in Minneapolis as T3, which stands for Timber, Technology, and Transit. It was considered the first modern tall wood building in the United States. It is, however, within the limitations of the International Building Code at the time it was built. It was not considered very tall at that time. You'll notice in this photograph that not all of the structural elements are made of wood. You'll see that there's an elevator and stairway core, as well as the parking level and the foundation of the structure made out of concrete type 1 construction. So some people refer to this as a hybrid building, a combination of non-combustible type 1 in this case, and the type 4 mass timber. This is a rendering of the interior of T3. And according to the information that I have, this building did not require any special local approval. It has an efficient structural system, and it's about 1/5 the weight of a similarly sized concrete building. So that has an effect on the foundations. So in addition to being made from sustainable lumber, which in this case looks very warm and inviting, it's also less energy intensive to extract these materials. And this building is estimated to sequester about 3,200 tons of carbon. This next photograph is that of a mass timber building recently completed in Vancouver, at the University of British Columbia. It's one of the tallest mass timber buildings in the world. It's 18 stories and provides housing for more than 400 students, as well as including some amenity spaces. This is a hybrid structural system comprised of CLT floor slabs, that is cross-laminated timber, glue-lam columns, steel connectors, and concrete cores. This building stands about 53 meters tall. I'll come back to that in a minute. In February of 2018, Sumitomo Forestry in Japan revealed plans for what's going to be the world's tallest building in Tokyo, and that would also be Japan's tallest building. It's called W350 in honor of the firm's 350th anniversary that will occur in 2041. They think quite far in advance. This is a 70-story, 350-meter high building, very tall. So when we talk about mass timber construction today, what do we mean by that? In our ICC committee work, we use the term mass timber in a broad sense and included a new definition for it in the 2021 code. Mass timber includes what we've known as type 4 construction, traditional heavy timber buildings, but also includes glue laminated timber, nail laminated timber, dowel laminated timber, and cross laminated timber, often referred to as CLT. The traditional heavy timber building is an example shown in this photograph on the left. It's a type of construction where the fire resistance of the structure is obtained by using minimum sizes of wood structural members and minimum thickness of wood floors and roofs, and traditionally does not include concealed spaces under the floors and decks. Looking in the model building codes today, you'll see that heavy timber construction has been given favorable treatment in its allowable area and number of stories. It's on par with that of type 2A construction. This illustration on the right of this slide is one of the illustrations that was in one of the books I used in school, and it illustrates the components of a heavy timber building very nicely. Now, additional types of mass timber that I mentioned earlier include glue laminated timber. That's a product that's been around for many years. It's composed of individual wood laminations that are bonded together with durable and moisture-resistant adhesives. In that case, the grain of all laminations runs parallel with the length of the member. Although it can be used in horizontal applications as a beam or vertically as a column, it has very good strength and stiffness properties, and pound for pound is stronger than steel. Nail laminated timber is created by fastening together individual lumber components stacked on edge and nailed together as it sounds. It is used in floors, decks, and roofs, and also used for elevator and stairway shaft walls. Dowel laminated timber, not pictured here, is similar to NLT, but wood dowels are used in lieu of the nails so that you have a totally wood product. In both NLT and DLT, sheathing can be added to one side to provide a structural diaphragm and allows the panels to be used as wall elements. CLT, cross-laminated timber, is a panel consisting of 3, 5, or 7 layers of dimensional lumber oriented at right angles to one another, as shown in this illustration, and glued together to form structural panels with exceptional strength, stability, and rigidity. CLT can be manufactured to any customized dimensions. Panel sizes vary by manufacturer, while the length is usually limited by the ability to transport via truck or other type of transportation. So why mass timber? Well, there are a number of things that are driving the demand for mass timber buildings today. Wood products are made from renewable resources found abundantly in North America. In addition to the environmental benefits of building with wood, there are some cost reductions that help offset the additional cost of the materials. The T3 project in Minneapolis that I mentioned included 180,000 square feet of timber framing and was built in less than 10 weeks. The Brock Common building in Vancouver has no exposed wood for aesthetic reasons, but that construction was selected because of the speed. That the structural parts of that building were completed in 66 days. And typically, the average time for construction for a mass timber building is about 9 days per floor. Product gets delivered to the site. There's very little storage of construction materials, and it's a very clean site typically. But what are some of the issues that were of concern to the Ad Hoc Committee on Tall Wood Buildings in the ICC? Well, from a fire safety point of view, the issues are pretty straightforward. There are some traditional principles that are of concern to the committee. Up to now, combustible construction was essentially phased out in high-rise buildings by the building codes. Generally, any type of building with a combustible structural system was limited to 7 stories. And for these reasons, limiting the fuel load reduces the risk to building occupants. As the building gets taller, they need longer evacuation times. And similarly, it facilitates firefighting in a more difficult building geometry as firefighters need to reach the taller buildings. So in this case, there's a demand to reduce the probability of structural failure for tall buildings. And this should be obvious. High-rise building fire safety depends in part on what we call a defend-in-place strategy, where people are allowed and expected perhaps to remain in the building, but that means we have to reduce the risk of collapse to allow people to stay in place, to allow intervention by firefighters, and also to reduce the risk of property damage to the building in question, as well as buildings that are adjacent, what we call the exposed properties. We've seen some structural failures in low-rise, non-combustible buildings that are unprotected structures, like single-story warehouses. But they are normally not a defend-in-place concept, and they normally don't injure building occupants or firefighters when that happens. But allowing that type of failure in a tall building is not acceptable. Another concern that I call being well connected. There has been a lot of discussion and concern about the structural elements in a mass timber building. The connections shown here are classic cast iron caps on columns where the columns and beams tie in. These exposed cast iron elements do not have substantial fire resistance and would not be suitable for use in a multi-hour fire exposure. They have historically not been much of an issue, but they're concerned as the buildings get taller and where we have a defend-in-place strategy, and the building elements are expected to survive a complete burnout of fuel and continue to support the structural loads. And that is normally considered without the benefit of automatic sprinkler protection. So there are systems that protect these connections in these taller mass timber buildings, either by embedding the connection within the wood or through an exterior barrier or coating or covering. And I envision that there will soon be laboratory listings of these connections that will make it easier for the design community as well as the enforcement community to select approved connection methods. Another issue that we've seen as a result of some early testing The 2015 edition of the IBC recognizes CLT products when they're manufactured according to an industry standard, a product standard called PRG 320. And there are various adhesives that are used to manufacture CLT. These adhesives have been used in glulam for many years, like I mentioned earlier. But some of the early fire tests that I'll talk about shortly revealed some concerns about the performance under long fire exposures of these adhesives. So our committee embarked upon a follow-up series of fire tests, and as a result of that, a new version of the product standard PRG 320 was developed, and I'll talk about that a little bit later. So those are some of the major issues that our committee faced before we even got started. So I want to talk a little bit about the work of the Ad Hoc Committee and how we develop what is now in what will be the 2021 edition of the IBC. So in late 2015, the ICC Board of Directors appointed an ad hoc committee to explore the science of tall wood buildings, to review the literature, to look at fire tests, and ultimately develop language for incorporation into the IBC. So our first meeting was held in the spring of 2016. Our committee consisted of 17 voting members, and of those 17, 2 were engineers. I was one of those engineers. 4 building officials, 3 fire officials, 2 architects, 5 industry representatives, and 1 testing organization, Underwriters Laboratories. There were also several dozen other interested parties who participated in the effort with their comments, their input, and in their overall help with the committee over about a 3.5-year period. At our first meeting, we established some performance objectives concerning what we expect from tall wood buildings. First, that there would be no collapse under reasonable scenarios of a complete burnout of the fuel without automatic sprinkler protection or manual firefighting being considered. There would be no unusually high radiation exposure from our building, the tall wood building, to any adjoining properties that would present a risk of ignition of adjoining properties under reasonably severe fire scenarios. Third, there would be the reverse of that, no unusual response by the tall wood building to a radiation exposure from a fire from an adjoining property that might ignite the tall wood building. Fourth, there would be no unusual fire department access issues. Fifth, that we would have an egress system that would protect building occupants during an escape time, including a factor of safety. We are not using a defend-in-place strategy here. And finally, number 6, that our fire suppression system should be highly reliable to reduce the risk of failure during reasonably expected fire scenarios, and that the degree of that reliability should be proportional to the evacuation time and to prevent the risk of structural collapse. So we had quite a bit of work to do. Our committee was divided into several subcommittees we referred to as working groups. This is a list of the working groups we had. There were dozens of meetings and conference calls over the period of our work, and involved about 100 people over the course of this 2.5-year period. All meetings were open to the public. All activities were documented on the ICC website, and that website is still available for review to see what we looked at, as well as some of the working drafts of our work during that 2.5-year period. Now, one of the things we talked about in our committee was that all of the code change proposals we developed would have their foundation based on actual fire tests. And one of our work groups here, you'll see the Fire Performance and Fire Test Work Group, was responsible to develop the fire test criteria going beyond tests that we received from the NFPA a couple of years earlier that left some questions in our minds. So our committee essentially directed a second full-scale fire test program sponsored in part by the U.S. Department of Agriculture and the American Wood Council, and conducted at the Alcohol, Tobacco, and Firearms Fire Laboratory in Beltsville, Maryland. So again, our objective was to submit technically based code changes for the IBC code change cycle, which was coming up in January of 2018. There's the deadline for the 2021 edition. So as I mentioned, our committee directed that the industry conduct a second series of fire tests with a bit more relevance to the issues of concern to our committee. The work group was operating parallel to other work groups, reviewing literature, taking testimony, and reviewing the current edition of the IBC to see what was needed to be modified as we proceeded with our technical analysis. Back to the fire test. This is a sketch, a floor plan of the simulated residential unit at the Alcohol, Tobacco, and Fire Lab. It was a two-story space, and you can see it's an apartment that simulates a two-room apartment with living room, bedroom, bathroom, kitchen, and also includes a corridor and a stairway. And we did that for purposes of determining what the environment would be like for responding firefighters. Now, this is a summary of the 5 tests that we did in some of the major parameters. Test 1 we considered a baseline test with all the walls and ceilings covered with 2 layers of gypsum wallboard. Test 2 was the same, but had 1 wall of exposed wood. Test 3 was the same as test 1, but had 30% of the ceiling area exposed. Test 4 employed automatic sprinklers operating in a conventional manner with fully exposed walls and ceilings. Test 5 was similar to test 4, but we included a delayed operation to simulate what would happen if the sprinkler system was out of service and the fire department, upon their arrival, would use the fire department connection to provide water to the fire. So this photograph is of the simulated dwelling unit in the Alcohol, Tobacco Fire Test Facility. You'll see the openings on the second level are blocked off because we did not want to damage the spaces in the second level by the fire test. You'll see we ran on the first floor in one of these tests. This is a photograph of the simulated dwelling unit loaded with typical combustible furniture in each test. And this fire load was determined based on a study of typical residential fire loads. You'll see this looks pretty crowded, and there are wood cribs, as we call them, in the space to get to the fire load that we wanted to achieve as a target. This is what that fire test looked like. One of the fire tests looked like at its peak. Again, the first 3 tests we did had no intervention, no automatic sprinklers, no firefighting. And these essentially were allowed to burn themselves out while we were collecting all kinds of data on temperature, carbon monoxide, heat release rates, and other parameters. If you're interested, you can see the videos of these tests on the ICC website in a high-speed format, so you don't have to spend 2 hours to watch each test. But I think it provides some very nice insight into what we were achieving and the data that we obtained. In fact, the reports themselves are available on the ICC website. In this next photograph here, you'll see what one wall that's flaming, that is obviously a test involving an exposed wood wall. And in this slide, you'll see 2 photographs of post-fire. On the left, you can see where there was part of the ceiling exposed, and where it's not singed is where that was protected by gypsum board. And in the photograph on the right, that's obviously an exposed wall condition following the test. So going back to what the 5 tests that we did, I want to emphasize that this is and I think this is important, it's a recap of the tests involving automatic sprinklers. Test 4, sprinklers operating in a conventional manner. The results were as expected. There was no remarkable heat exposure or damage to the unit. In test 5, after that 22.5-minute delay, simulating an inoperable sprinkler system, the fire was promptly extinguished as the water operated from the open sprinklers. So overall, the sprinklers performed well in both tests. So while the fire tests were underway by one of our subcommittees, the technical committee also went through, another subcommittee, the one that I chaired, went through a thorough review of the entire IBC and identified about 100 potential sections of the code that could be affected by the construction of taller mass timber buildings. This is an example of a matrix we used. We went through those 100 sections of the code, and this work went on for many months. In the end, we developed 14 major code changes to allow taller and larger mass timber buildings than what were currently allowed in the 2018 edition. And this is a summary of those major changes. I won't get into all these, but we'll get into them and more, and we'll highlight the major changes shortly. This is a summary of the timeline that the committee went through. We started in January. We started so that we'd be finished meeting the deadline to get the January 18 code changes proposals. The IBC divides its code changes into what's called Group A and Group B, the various chapters of the code. So we submitted the 14 changes for the Group A proposals in January. They were heard by a committee, public hearings in April, further public hearing in October, and in December of 2018, after passing the vote of the committee and at the public hearing, the online vote of the ICC members approved the Group A code changes. In 2019, the Group B changes, which are related to some of the structural provisions, went through the same process. And in fact, just a week ago at the ICC, the Group B changes were voted on, and yet we're waiting for the full vote of the membership, and that's expected to pass as well. So now we'll get into some of the major changes, and I'll pass it on to my colleague, Tim Costello.
Thank you, Carl. So what's changed in the 2021 IBC? So to start, we'll discuss what's in the 2018 International Building Code. The 2018 International Building Code includes 5 main construction types. Type 1 and 2 are non-combustible. Types 3 and 5 have lightweight combustible framing. And type 4 is what is known as traditional heavy timber construction that Carl mentioned previously. The subtypes A and B also provide for different fire resistance ratings for the key building elements within the major construction types. The changes in the 2021 edition introduced 3 new subtypes of type 4 construction: type 4A, 4B, and 4C. What was known in the 2018 edition as type 4 is now called type 4 HT for heavy timber. These new subtypes were the result of market demand, with some designers and owners wanting the wood aesthetic and others wanting to achieve carbon sequestration. The 3 new subtypes of type 4 construction are significant in that they are based on fire resistance ratings rather than the minimum dimensional lumber sizes previously applicable to type 4 heavy timber construction. A fundamental principle adopted by the Ad Hoc Committee on Tall Wood Buildings was to leave the 2018 IBC requirements for type 4 heavy timber alone. Therefore, the values for type 4 heavy timber in Table 601 remain unchanged. Highlighted in red are the required ratings for the structural frame, walls, and roof. The minimum ratings for the primary structural frame and bearing walls for type 4A construction are 3 hours, and types 4B and C are 2 hours. Floor construction is 2 hours, and roof construction is either 1 hour or 1.5 hours. The primary difference between each new subtype relates to the amount of exposed wood surfaces that will be permitted. Exposed mass timber surfaces will not be permitted in Type 4A construction, while Type 4B will allow for a portion of the mass timber surfaces to be exposed. Type 4C will allow fully exposed wood surfaces similar to Type 4 heavy timber construction today. Accordingly, Type 4A buildings will be allowed to be taller and larger than Type 4B, and Type 4B larger and taller than Type 4C. The fire resistance rating of mass timber structural elements is required to be determined based on the fire resistance of the mass timber element itself, which can be calculated, plus the rating from non-combustible protection that is applied to it. Chapter 16 of the American Wood Council's National Design Specification includes information on how to calculate the fire resistance of CLT, NLT, glulam, and solid sawn lumber, and is a great resource for these designs. In addition to meeting the required fire resistance ratings identified in Table 601, all mass timber elements must also meet certain minimum sizes. These sizes are those historically used for heavy timber in prior editions of the IBC, and they can be found in Section 2304.11. Being conservative, for mass timber elements, 2/3 of the required fire resistance rating must be provided by passive protection that's offered by non-combustible coverings, such as gypsum board. For example, where a 3-hour rating is required for Type 4A construction, at least 120 minutes of that rating must come from passive protection. To aid in determining the amount of protection afforded by typical non-combustible materials, Section 722.7 was added and includes a prescriptive table similar to this one identifying the amount of protection provided. This section also details the method of attachment, finishing, and edge treatment where bordering on exposed mass timber areas. As an example, 1 layer of Type X gypsum wallboard will afford either 30 or 40 minutes of protection depending on its thickness. 2 layers would provide 80 minutes. In addition to the prescriptive fire resistance method described in Section 722.7, Section 703.8 was added to provide for a performance-based approach. This will allow designers to provide non-combustible protection using other materials or assemblies based on the ASTM E119 fire test procedure to determine the time contribution of the non-combustible protection to the fire resistance rating of the overall mass timber element. This table is a summary of the fire resistance rating requirements for the structural elements of the 3 new construction types. Again, while the ratings for Types 4B and 4C are both 2 hours, the wood elements in Type 4B have some limits on the amount that can be exposed, while most of the wood elements in Type 4C can be fully exposed. Here are some additional details on other elements of the building requiring non-combustible protection. Please note that no exposed combustibles are permitted on the exterior walls in any of these 3 types of construction. A significant concern during the code development process was building height. Unlimited heights are not permitted with mass timber construction. The current maximum height is 18 stories for residential buildings and 18 stories for business occupancy buildings. This table is a summary of allowable height in feet, allowable number of stories, and allowable area per story for each of the construction types and for some common occupancy types. Each of these examples is based upon a fully sprinklered building. Note that the maximum area per building is 3 times the maximum area per story. The height and area tables in the IBC are not scientific. Professional judgment involving a multiplier is used to develop the height and area requirements for Types 4A, 4B, and 4C construction, with the heights or areas of some occupancies then reduced based on relative risks. The rationale employed is discussed in more detail on the following slides. For Type 4A construction, the height and story limits are 1.5 times that provided for Type 1B construction, which is commonly known as 2-hour protected fire-resistant construction. Note that the fire resistance ratings required for Type 4A construction are equivalent to that of Type 1A construction or 3-hour protected construction, making this a conservative multiplier. Type 4A construction will allow for the tallest mass timber buildings at 18 stories and 270 feet in height. Similarly, using a ratio, the area limit for Type 4A construction was generally 3 times the area limit for Type 4 heavy timber. As mentioned, the resulting values were reduced for higher risk occupancy such as high hazard and institutional. As described earlier, Type 4A construction requires all of the mass timber surfaces of structural elements to be provided with passive protection. Other elements like floor surfaces require a minimum of 1 inch of non-combustible protection. Exterior walls require at least 2 layers of 5/8 inch gypsum wallboard on the inside surface and 1 layer on the exterior surface. The height and story limits for Type 4B construction are the same as those permitted for Type 1B construction. The area limit was generally 2 times the area limit for Type 4 heavy timber. Again, in a number of cases, the committee reduced the resulting values to be more conservative, like for high hazard and institutional occupancies. In Type 4B construction, non-combustible protection is required on the surfaces of all mass timber structural elements with limited exceptions for exposed areas. These photos show how these limited exposed surfaces can be used to achieve aesthetic effect. The amount of exposed mass timber surfaces is given as follows. Any mass timber beams and columns that are not integral to the walls or ceilings may be exposed. As an example, the column in the foreground in the picture would be not integral to a wall, therefore it's allowed to be fully exposed. Otherwise, mass timber ceilings and beams may be exposed up to 20% of the floor area of the dwelling unit or the fire area in which it is located. Or walls and columns may be exposed up to 40%. Or you can have a combination thereof. The calculation for mixed unprotected surfaces, including both ceilings and walls, is shown by this equation. As an example, for a dwelling unit that has an area of 1,000 square feet, up to 200 square feet of ceilings and integral beams can be exposed, or 400 square feet of walls and integral columns can be exposed. If a combination of exposed walls and ceilings is desired, then the exposed surface areas of each must be reduced per this equation. In this example, we are using 50% of the permitted amount of exposed surfaces for both ceilings and walls. If the actual amount of exposed ceilings is increased, the amount of exposed walls must be reduced accordingly. There is also a limit on how close exposed mass timber surfaces may be to other adjacent exposed mass timber surfaces. A minimum of distance of 15 feet is required. This is measured horizontally along the ceiling or the floor. The combination of area and adjacency limits exposed mass timber surfaces is conservative and does not take into account the benefits of automatic sprinklers. However, this conservatism was the consensus of the committee and what was approved up to now. More fire tests might benefit this issue in the future. Similar to Type 4A construction, non-combustible protection is required for mass timber floors, roofs, and exterior walls in Type 4B construction. In this case, the floor surfaces require a minimum of 1 inch of non-combustible protection, and the roof requires 1 layer of 5/8 inch Type X gypsum wallboard on the inside face. And the exterior walls generally require at least 2 layers of 5/8 inch Type X gypsum on the inside surface and 1 layer on the outside surface. For Type 4C construction, the height limits are the same as they are for Type 4 heavy timber, but more stories are allowed because of the enhanced fire resistance rating of 2 hours. The area limit multiplier was generally 1.25 times the area limit for Type 4 heavy timber. Again, in a number of cases, the resulting values were reduced to be more conservative for certain occupancies. In all cases, no increases were granted for unsprinklered buildings in the new categories. For Type 4C construction, similar to Type 4 heavy timber, all mass timber surfaces are permitted to be exposed. However, there are some limitations that differ from Type 4 heavy timber, including required protection for shafts, concealed spaces, and the outside face of exterior walls. Unlike Types 4A and 4B, non-combustible protection is not required for the floor surface and roof surfaces in Type 4C construction. However, the minimum 1 layer of 5/8 inch Type X gypsum wallboard is required for the outside surface of exterior walls, while no protection is required for the inside surface. This takes into consideration the building heights, which are the same as permitted for Type 4 heavy timber construction and are within the reach of fire department aerial apparatus. This graphic, which was prepared by Susan Jones of Atelier Jones, shows the advantages of increasing protection for mass timber surfaces and fire resistance in terms of height and area for a hypothetical business occupancy building. Full advantage of the architectural aesthetic provided by exposed mass timber surfaces can be realized through the use of Type 4C construction, but the building heights and areas will be most limited. Where the focus is on carbon sequestration, full protection of mass timber surfaces will allow for a substantially taller and larger building by using Type 4A construction. Where the project goals include a combination of aesthetic and carbon sequestration, Type 4B construction provides an intermediate solution, although the amount of exposed mass timber surfaces is limited and requires careful coordination to ensure adequate horizontal separation. In addition to the major changes related to construction classification, fire resistance, height and area, the 2021 IBC will include modifications to address other aspects of the tall wood buildings. During construction, special inspections will be required to ensure proper construction of the mass timber elements. This will include verification that the proper adhesives have been used. Taking lessons from lightweight wood construction, the 2021 International Fire Code will include provisions for minimum water supply at the site during construction and maximum number of stories allowed to be built before the required non-combustible protection is installed. Once the building is occupied, another provision will require that the building owner maintain an inventory of fire resistance rated mass timber assemblies and ensure that they are properly maintained over the life of the building. This, of course, will present its own challenges, particularly in residential buildings. As Carl mentioned, during the fire test, where fire compartments were constructed of CLT and allowed to free burn to self-extinguishment without automatic sprinklers and without manual intervention, delamination of CLT layers was identified as an issue. Falling to the floor, these delaminated sections would rekindle and allow subsequent delaminations. It was clear that the adhesives were not performing as desired. The 2018 edition of PRG 320 added new elevated temperature performance requirements for these adhesives used in CLT elements. The 2021 IBC specifically requires compliance with the revised edition of PRG 320 to ensure that suitable adhesives are used for CLT members. Another lesson learned from the NFPA fire test was that there was air movement through the joints of mass timber elements. To address this, sealants are required to be provided that meet the requirements of ASTM C920. Adhesives must meet the requirements of ASTM D3498. The exception to this requirement is where a sealant or adhesive is not a required component of fire resistance rated assembly. Concealed spaces are somewhat of a sacred item preserved from prior editions of the IBC. Part of the successful fire performance of heavy timber buildings is that concealed spaces are not permitted. The heavy timber construction of such buildings is open, providing no place for fire to initiate and grow without being easily seen. Should a fire occur, it is not extraordinarily difficult to extinguish due to lack of concealed spaces. Yet, realistically, there will likely be some residential and even business uses in new mass timber construction. These types of occupancies often have significant amounts of mechanical, electrical, and plumbing components. To accommodate this, concealed spaces are permitted in types 4A, 4B, and 4C construction, as long as they contain only MEP systems and the concealed spaces are provided with non-combustible protection of at least 40 minutes in fire resistance in type 4C and 80 minutes in types 4A and 4B construction. In terms of shaft enclosures, stair and hoistway shafts up to 12 stories or 180 feet in height can be constructed of mass timber that is protected with non-combustible materials to achieve the appropriate rating based on the shaft height. Non-combustible shafts are required for mass timber buildings over 12 stories or 180 feet in height. Sprinkler system reliability was considered important in tall type 4 buildings. Therefore, the new code provisions include a requirement for 2 water supply mains serving the sprinkler systems in buildings over 120 feet in height. As a comparison, 2 sources are required in type 1 construction that is more than 420 feet in height. Again, a bit more conservatism was employed for occupancy separations with this provision. It requires that mass timber elements serving as fire barriers or horizontal assemblies that are used to separate occupancies in types 4B and 4C construction be separated from the interior of the building with at least 1/2 inch of gypsum wallboard or equivalent non-combustible material. Finally, as the designs using mass timber are developed, the details of how to penetrate fire resistance rated floors and walls must be resolved. At this time, there are a limited number of listed fire stop assemblies for items penetrating CLT panels. Woodworks has published a list that you can view on their website. Note that these listings are for CLT and not NLT, DLT, or other methods of creating mass timber panels. The listings are very specific and generally limited to single penetrating items or single cable bundle. You can seek engineering judgments for other conditions to the extent that the fire tests and similar listings support them. Now I'll pass it back to Carl for an overview of a case study.
Thanks, Tim. In this particular project in Cleveland, Ohio, we were given an interesting challenge by the client who wanted to develop an 11-story office and an 8-story residential building on a site that's kind of in a trendy area of the city. Of course, at this time, the issues are that there's no currently adopted code that would allow this type of construction. So we had various discussions with the local authorities to bring them up to speed on the 2021 edition of the IBC, and they were open to that concept. One other issue is that the architect wanted to expose up to 50% of the mass timber buildings, but the building was taller than what would be allowed for type 4B construction. So we analyzed relevant fire tests that were directly comparable to that design, and we also identified some enhancements that provided the local authorities an additional degree of confidence that the risk was acceptable. That project approval took about 3 months, and so we consider this to be a very successful case study for the client and for the city. So in summary, we hope you've had a nice introduction to what's going to be in the 2021 edition and why the code provisions were developed. And at this point, we're able to take your questions. Thank you very much.
All right, thank you, Carl. Thanks, Tim. As a reminder, if you have a question, please type it into the Q&A box and hit send. If you've already submitted any questions through chat, we'd appreciate if you would copy and paste those into the Q&A box. If we don't get to your question during the call, Tim and/or Carl will follow up with you afterwards. So now let's go ahead and take our first question. I'm an architect and have a client considering a mass timber building design with exposed wood in the units, but it's taller than the new code will allow for using exposed wood. How can I get that approved?
I'll answer that. That's very similar to the case study we just mentioned. There are strategies that we develop that are over and above the minimum code requirements. And it's also a matter of meeting minds with the local authorities about the background of what caused the requirements in the 2021 to be as they are, an understanding of the fire test. So a combination of some discussions and information sharing, as well as incorporating some enhanced features, should be able to allow that kind of a design.
Okay, we'll take our next question. What are the distinctions in the 2021 code between type 4C and type 4 heavy timber?
Liz, I'll take that.
Okay.
Okay. Thank you. Yep. The primary differences are the number of stories are increased for type 4C construction, although the heights are the same, maximum height. In addition, we talked about in the slides I was going through that the type 4C construction is allowed to have concealed spaces as long as they're limited to MEP components and they have the non-combustible protection for those concealed spaces. So those are two significant differences between the two types of construction. Additionally, the type 4C is considered to have a fire resistance rating of 2 hours for the major components, whereas heavy timber construction is based upon the dimensional dimensions of the heavy timber components.
Okay, the next question is, has the committee considered the CLT delamination issues observed at the Oregon State PV Hall project, and how is this addressed in the new code update?
The committee was made aware of that incident, and the committee was quite concerned about that. It is considered a product failure for various reasons that I won't go into here because I know there is some litigation involving that project. But that was considered an abnormal condition and would not normally be expected with products that are built to the PRG 320 standard. Leave it at that.
Okay, our next question is, this may be an NFPA 13 question, but for the concealed spaces with the different types of construction, would the protection be required in the concealed spaces to eliminate the need for sprinklers? Is it even acceptable to have exposed CLT or other timber in the concealed space?
If the concealed space is protected in accordance with the provisions of the IBC, automatic sprinkler protection could be eliminated in the concealed space, but it would not work the other way around. Providing sprinklers in the concealed space would not eliminate the need for the passive protection. So that is an additional bit of conservatism the committee wants to maintain.
Okay, next question. How are wind-driven fires taken into consideration with external or internal exposed wood?
I can take that too. First of all, there is no external exposed wood permitted in the IBC provisions, and that was a very important thing that the committee wanted to make sure. During the work of the committee, while we were meeting, the Grenfell Tower fire in London occurred, and that was considered a pretty important fire in our work that we said we're not going to go there. So there's no exposed exterior wood permitted. But this issue of wind has been brought before our committee and how it affects fire tests. And I mean, the same thing is true for any type of construction of a building of any height. So until the test committees want to bring up the issue of wind-driven fires in tests, that's something that our committee is not going to deal with.
Tim, did you have anything you'd like to add to that?
No, I think that is a pretty accurate statement. I just want to address a separate comment, question that came up in the comments that was related to one of the slides I had. The question was, is there, for type 4B construction, is that permitted for occupancy group R1, which would be like hotels? And yes, it is. It's permitted for all of the occupancies. The tables that we had in the presentation were just highlights of the tables that are in the codes. They weren't complete reproductions of the tables in the code.
Okay, fantastic. So that looks like that's all the questions that have come in right now. If anyone has any other questions, of course, feel free to reach out to Tim or to Carl with any follow-up. We will send you all an email probably tomorrow morning that will include a link to a recording of the webinar as well as instructions on how to request credit for your participation. And that will include contact information for Tim and Carl if you do have any other questions. So we really appreciate your time today. We hope it's been educational. Please join us again, and we hope you have a great rest of the day.